Here I want to discuss the characteristics of what are called the hydrogenic atomic orbitals, these wave functions that satisfy the Schrödinger equation for the hydrogen atom system. They're called atomic orbitals since they're relevant to the atom. In particular, I want to talk about the orbital concept in general, ideas that are going to apply to orbitals wherever you see them, atomic, molecular, what have you, and then look more specifically at the shapes of the hydrogenic atomic orbitals, which, for reasons we'll see later, can also be applied as orbitals of heavier atoms. So the orbital as a concept. As I mentioned at the end of the last video, you'll see orbital energy diagrams like this over and over and over again. The thing to notice about diagrams like this in the bottom left-hand corner of the slide is that energy is increasing as we move from bottom to top, and each line is an orbital. Each line is a wave function, in this case, that satisfies the Schrödinger equation, and the corresponding energy is just related to the vertical position of each of these horizontal lines on the graph. So we've seen that the hydrogenic orbitals are characterized by these quantum numbers, n, l, m sub l, and s. These numbers affect one of the essential properties of the orbital, which is its energy. How stable is an electron characterized by, or we often say occupying or sitting in, that orbital? The shape of the orbital is a second fundamental property, and that is the shape of the wave function in three-dimensional space, how it varies in three-dimensional space. If we could graph, and this would be difficult to do, but if we could graph the value of the wave function at every point in three-dimensional space, what would it look like? That's the shape of the orbital. And it characterizes where electrons in the orbital are likely to be located, right? Remember this idea that the probability of finding an electron at a particular point is equal to the wave function squared at that point. And so when psi is large, the electron is likely to be located at that point in space. The final fundamental property of every orbital, in addition to energy and shape, is the occupancy of the orbital. Orbitals may be occupied or unoccupied. For example, in the neutral hydrogen atom, in its lowest energy or ground state, there's one electron in the 1s orbital. The electron can jump up to these higher energy levels, and that's the origin, actually, of the discrete absorption spectrum of hydrogen, right? The electron can jump up. But in the ground state, these empty orbitals are called unoccupied because they don't have electrons within them. And so for every orbital, for each of these horizontal lines, remember, each one of them is an orbital, we can ask the question, does it have electrons in it or not? Simple as that. If it does, it's occupied. If it does not, it's unoccupied. And these are the three fundamental properties of every orbital. I want to emphasize that even though we've developed the concept of a wave function in an orbital in a hydrogenic context, in the context of the hydrogen atom, these properties, energy, shape, and occupancy, are fundamental to every orbital. And you should ask for every orbital or orbital energy diagram you come across, what are the energies, what are the occupancies, and what are the shapes? Occupancy and energy we can read directly from an orbital energy diagram like this, right? So for, again, to use the hydrogen atom as an example, a single electron, here we can see that the 1s orbital is occupied, all the others unoccupied, and the energies we can see based on the position of each line on the graph. So the 2s orbital is higher in energy than the 1s orbital, for example. That leaves open the question of shape, and shape is usually not represented on an orbital energy diagram. It's important actually to internalize the shapes of the hydrogenic atomic orbitals. They're not terribly complicated, but it takes some practice and I think some drawing to actually internalize these shapes. So next we're going to look at the typical shapes of especially the s, p, and d orbitals, and we'll look briefly at the f orbitals as well. This Orbitron website is a great resource for learning the shapes of the atomic orbitals. And let's start at the beginning and look at the shape of the 1s orbital first. The 1s orbital is basically spherical. Inside the sphere, there's a high probability of finding the electron. Outside of the sphere, there's a low probability of finding the electron, and the size of the sphere is dictated by some cutoff value. That, by the way, is a pattern that we'll see throughout our studies of orbitals. When we look at orbital shapes, inside the surface of an orbital shape is a high probability of finding the electron, and there's a lower probability of finding the electron outside of that shape. So the 1s orbital is basically spherical and is very close to the nucleus. If we move to the 2s orbital, we get a larger sphere. In fact, S for sphere you can see that all the s orbitals are spherical. Something interesting is happening inside the orbital. We go from kind of a shell of wave function that's blue to an inner core of wave function that's red. And what's happening here? Well, remember that the wave function is just a number. It's just a function, right? And numbers can be positive or negative. So in orbital shapes where you see different colors, that indicates different signs. Different colors indicate different signs for the wave function, positive or negative. That has nothing to do with charge, which is a common point of confusion. But here, what we're seeing in the 2s orbital is the wave function goes from negative to positive as we move outward from the nucleus, or positive to negative, if you like. It's really the relative comparison of the two colors that's most important, and not necessarily which is positive and which is negative. In fact, think in terms of waves, right? Waves have negative regions where they're in troughs and positive regions where they're in crests. The wave function works the same way, and when wave functions overlap, when wave functions interfere, the negative and positive regions become very important to help us understand whether constructive or destructive interference is going on. This kind of shell of space where the wave function must be zero if it's going from negative to positive, for example, is known as a node. And the idea and concept of a node is very important, and as you'll probably see as you study orbitals down the line, the number of nodes within an orbital is related in a deep way to its energy. If we move from L equals 0 to L equals 1 at the level of n equals 2, we get to the 2p orbitals. And the 2p orbitals have this kind of dumbbell shape. Here the two different signs are represented as green and blue instead of red and blue, but we see that there are now 3 2p orbitals, since m sub l can be +1, 0, or -1, and these correspond roughly to the 3 cardinal directions. So here's the pz, here's the px, and here's the py orbital. Electrons in these orbitals are likely to be found kind of above or below the nucleus. The nucleus, by the way, in all of these drawings is sitting at the origin. If we look at the 3s, we in fact see another node coming in. We go from positive to positive within the 3s orbital. The 3p orbital also contains additional nodes. So there's still a node at the nucleus. That's actually an important thing to note about all of the p orbitals. They all include a node at the nucleus, but there's also a node where the density goes from kind of gold to pink within each of the sort of ends of the dumbbell, so to speak. We still have 3 atomic orbitals within the 3p subshell because m sub l can still only be -1, 0, or 1, and they still roughly correspond to the 3 cardinal directions. The most important impact of stepping in up from 2 to 3 is that we've introduced additional nodes into the orbital. The d orbitals begin at the n equals 3 level, and here they are. Now there are 5 because m sub l can be -2, -1, 0, 1, or 2, but they do have their own sort of mathematical names. There's x squared minus y squared, z squared in the top right, xy in the bottom left, xz in the bottom middle, and yz in the bottom right. You can see that especially along the bottom, variables used correspond to the plane in which we find the orbital, right? xy is found mostly within the xy plane. Looks kind of like 2p orbitals smushed next to each other. And if we step up the n value from 3 to 4, the same basic shapes actually prevail. We just get more nodes within. So each lobe now has a node within it when we move from n equals 3 to n equals 4, but the same basic shape is still there. We can still recognize, for example, this kind of vertical with a donut around its shape as the dz squared orbital. And finally, we'll just briefly look at the 4f orbitals, and I won't have too much to say about these, except that notice that there are 7 of them, and that's consistent with the possible m sub l values from -3 to +3. And we have a lot of nodes in these because we're very high energy, but the same basic idea applies, that as we move up to 5f, 6f, 7f, etc., the basic shapes still prevail. The shape is mostly dictated by the L value, the fact that it's an f orbital. The n value only affects the number of nodes and thereby affects the energy. That's true regardless of whether we're talking about s, p, d, or f orbitals.